So, hi everyone, I'm Axel, I'm CTO at Uptime, and today I'll be talking about predictive maintenance and more specifically the journey that we took to build a predictive maintenance system at Uptime. I tried to extract some key learnings that we had along the way that might be useful to other people that are building similar stuff. But first, a few words about what's Uptime. We are a company founded in the end of 2016, and we are focused on delivering quality elevator maintenance. By quality, I mean actually committing contractually to delivering no more than 2 failures per elevator per year, done from a market benchmark of 3 to 5. The way we do that is by enabling our maintenance technician through internal technical tools. One such tool is the maintenance, predictive maintenance system that we are building, and it's really key to achieving the performance that we want to deliver to our clients. So before we dive into that, I'm not sure, okay, there's something missing in the middle. Try to cover it in the same way, but anyway, so just a quick refresher on predictive maintenance for those of you who aren't completely familiar with it. When you approach the problem of maintaining an industrial equipment, you have basically 3 approaches. The first one is reactive or curative. In this scenario, you just wait until the machine fails and then you go and repair it, either temporarily or definitely. Then you have a better approach, the preventive approach. You have some subcases, but the more generic one is to have scheduled preventive visits. So that's what's supposed to show in the second part. And if you're good, you are able to determine from the status of your equipment which parts are critical and likely to fail. And so you focus on these and are able to prevent breakdowns in the future. And the third approach, and the one we are trying to reach, is predictive maintenance. In that scenario, you have a sensor or other status data that act as leading indicators of your equipment's health. So you take this, you're trying to learn the behavior of the normal behavior of your equipment. It gives you some thresholds, and if those values exceed those thresholds, then you take some preventive action to avoid failures. So that's what we are trying to do with elevators here. The point here is that we won't, for the moment, be able to reduce the number of visits that we have to do because we are legally required to perform a certain number, 9 in France, for example. But we'll be able to focus through these techniques the actual work that the technician do. So that's why it's really key for our business. So now, how do we go about building such a system? The main component for us is to combine 2 data flows. On the right side, of course, you have the hardware sensor that we deploy on our elevators. We'll see a bit later what exactly this does, but basically it sends us some real-time IoT data about the status and the health of the elevator. The other part comes from the actual maintenance technicians in our team who are able to send to our system some normalized information about what they do. So by what they do, I mean what exactly they fix, what kind of failures they experience in the field, what kind of parts they replaced, that kind of things. In return, our system should be able to help them plan their maintenance visits and determine what exactly they need to focus on. The issue with that kind of a thing is that we are faced with the same chicken and egg issue that most startup faces. Meaning that to build a system, well, we need data. To get data, well, we need to have deployed hardware, of course. And to have deployed hardware, We need to have a big enough elevator portfolio. But to get this portfolio, we need to get some kind of competitive advantage over the competition, which is supposed to be our algorithms. So to get out of this, this potentially virtuous cycle, we took the, now standard lean principle and tried to build as fast as possible a good MVP that allowed us to deliver value to our clients as early as possible. The learning here is it's possible in those cases to really go fast and try to learn early with some kind of tricks. In our case, the trick was to hire early on some very senior technicians who really helped us both define the initial constraint of our product and bootstrap our elevator portfolio. In fact, it's way easier to perform quality maintenance when you have a small portfolio and when you have good technicians. The actual problems come from when you scale, when you have more of them. So with this initial prototype development, we were able to gather some really interesting insights about how to deploy that in the field, what kind of data we need, how we can deliver that to the clients and to our technicians. And this closed the loop and allowed us to start iterating. One key component in this whole system is our in-house maintenance management system. We took some time to actually reponder the make versus buy decision here, which was a huge one for us because it really takes some time to build something interesting here. But in hindsight, it was really a good thing for us. First, because by tailoring it specifically to the business processes of our maintenance team, we were allowed we allowed them to be way more efficient than with an off-the-shelf service. Then, because we are able also to control the whole pipeline of data from start to finish, we had some way better insights into what was really going on. And third, building this system between hand in hand between the product team and the maintenance team was really key in bonding them, which I see later is really key to building a good predictive maintenance system. So this brings me to my second point, which is that especially in cases where you have little data and little to start from, you really need to get as many and as much knowledge as possible from the actual business, in our case, from the maintenance technicians. That's some insight that we also took from other companies. For example, I'm not sure how many of you have heard of Kepler. One. So Kepler is a company that does communities tracking worldwide, and they use data science techniques to do that. The way they approached it to really build their product in the right way was to, instead of having product people be product owners and teach them the ways of the analyst, they took some product-oriented analysts and taught them the job of a product owner. So it made the product way better in that sense. So that's something that we are trying to do. But to illustrate that point, let's dive a little bit deeper into how an elevator works. Well, I guess you all know what this is, and I guess you all know the basics of how it works. But what's really important here is that most, if not all, of the intelligence of the elevator is concentrated in the control panel. Control panel can be below, above, or in some newer installation within the shaft. It concentrates all of the sensors that are within the elevator and acts as the brain of the system. What's good for us is that weird stuff. So what's good for us is that a few decades ago, elevator constructors starting putting in some diagnosis ports to help technicians debug what was happening in the field. And through these ports, we are able to get some sensor and actuator data and some error codes that are already computed by the control panel, and some usage statistics that can be pretty interesting for us. So that's exactly what our hardware module does. It takes that, put that in the cloud, and then we can analyze it later. The first deployment started somewhere around a year ago, and quite fast we saw that there was really value in it. At some point, for example, we were able to remotely determine that an elevator was failing, go there, check it, fix it, and go back before even the client had noticed anything. So this was one of the first big wins for us that pushed us to take this process and automate it as much as possible. One of the issues that comes from developing such a system is the sheer diversity of elevators that we have. First, because they are quite old, mostly more than 25 years old. And they had seen many revisions over the year to comply with new regulations. And they all, in some way, display some kind of specific behavior. So that makes the data part kind of hard to analyze. Furthermore, each specific vendor has its specific proprietary format of diagnosis and a specific way of sending in data. So we need to address all of those, and to give you an idea, here's a breakdown of all the brands that we cover with our modules. It's not even all of them because I've removed the less popular ones. So, to tackle this issue, like I said, we try to really work in hand in hand between the data team and the maintenance team. One really key and critical point for us was to hire a senior maintenance technician, and having built test benches for control cards and show to our engineering team how this works, how the business logic of the elevator is thought by its constructor, and exactly what we can extract from it as value. So it was really, really interesting for us, because that's something that you usually have only when you crawl through a vast amount of data before you actually learn something. So what we really did here is try to bootstrap our data science insights with specialized knowledge. Which brings me a bit further down the data pipeline and into the cleaning process. Well, I guess most of you know that cleaning up data is a good part of what a data scientist does, and sometimes it will take more time to actually do the actual cleanup than to design algorithms later on. This can seem like a really tedious task, but what we found is that in our case, having the data and business close together in this task can have really valuable outcomes, both in terms of data and in terms of business processes. Sorry, forgot something. If you want another example of a company that does something similar to this, you can check out Neighbor, for example. Neighbor, I'm not sure if you've heard of them. Okay, 0. But what's interesting in what they do is that they produce customized data sets, mostly based on geographical data. What they've learned is that this kind of data has many quirks and weirdness, and to address this issue, they made their data scientists work hand in hand with specialists of the field, so like sociologists and geographic analysts, and they helped them tackle the issue of random quirks. So in our case, it's not geographic data, it's operational data. and namely breakdowns. The issue with breakdowns, in our case and in most cases, it's that they are reported by clients through our customer call center service and then to our service, which means that there are many ways the data can be giving false positive, and for example, the timing is really unreliable. To give you a good example, a breakdown can take from a few hours to a few days to get reported, depending on the use of the elevators and other parameters. And also, some data can be mislabeled as a breakdown rather than just a lamp going on, and it's not really affecting the health of the elevator. Furthermore, if you look at the number of failures that we experience per year, even if you take only the market benchmark, you have from 3 to 5 per year, which is, well, way too many for users, which is why we're here, but also way too few for data scientists to actually extract data from. So what we did to address that is first design the cleanup process with the maintenance team. After all, they are the ones who really know what happened, when, at what time, and which kind of failure happened. Once we did that, we were able to extract some valuable insights into the business processes that we can put in place, and we set them up as close as possible to the actual breakdown and to the technician. Basically, what this means is that the technician and their manager work together to post-process the data in a way that makes it easier to understand later on. The beneficial side effect is that it helped them and helped us put in place some best practices borrowed from industrial maintenance, like doing root cause analysis in every case. From those insights, we were able to get some data that we validated as early as possible with the maintenance team. So that's just to give you an idea of how this works. On the right side, you have the back office of our maintenance managers, and on the right side, you have the field application that the technicians use to get the breakdowns and classify them later on. Which brings us to my last point. So last in line in the pipeline, which is that we really spent some time analyzing which kind of data science technique really apply to our use case. And that was really important to us. So the more specific ones here are that we transform the input data that we have into a time series and aggregating them with failures. That's really specific to us. What's a bit more generic is using explainable algorithms when you really need to work with non-data scientists. That helped us determine when the model was going in the wrong direction without having to refer to really complicated statistics that we didn't have access to in the beginning. And then we were able to use some really interesting methods to compensate for the imbalance of data, like oversampling. And that's something that we were able to do because our data scientists got really intimate knowledge of the data from the technicians in the field. And just a last point I wanted to make on top of that is the importance of tooling even in really early stage scenarios. Because we started like everyone else with just Jupyter notebooks and scikit-learn, which works really well. But we found out that having really good tools like Dataiku, for example, help us achieve way better efficiency while allowing us to historize what we do, collaborate on data, and basically being way more efficient. Like for the same task, we take 3 times less time with Dataiku. So last point, where are we going next to come from this failure detection system to an actual predictive maintenance system? Well, the first point is that the data scarcity issue that we have now will probably soon go away, because our portfolio is growing fast and the data set is growing even faster. But even without that, there are some techniques that we want to apply. First one being to analyze the traffic patterns and try and detect anomalies. The second thing that can be really interesting in our case is to target algorithms to specific parts of the elevator. For example, the doors are really important to us, and we know that with some data that we get, we are able to detect that the door specifically didn't work correctly and a specific component is failing. And finally, the last technique that we want to apply, borrowed from industrial maintenance, is vibration monitoring, which will allow us to be way more precise in the kind of failures that we detect. Right, that's all for me. Thank you for listening.
Excellent, thank you. Questions from the audience? So first one to start on my side. How do you collect the data today? I mean, so you're connecting yourself to the control panel?
Yeah.
But does that mean that you're able to connect real time, or you're collecting data only when the maintenance technician is going on the field?
No, it's actually real time. We use a 3G connection in the shaft to gather the data in real time, and that's really the strength of the system.
And just to complete my question on the vibration,
yeah.
Does that mean that you will need to add some specific device
exactly.
on the elevator? Because I guess today this information is not available.
Yeah, it isn't. But there are two ways we can look at it. We can put some specific devices in the cabin because there are some failures that we can detect there. For example, the guides can be a bit misaligned, and that can be a real big issue. But smaller, I guess, if it's taken early on. Or we can put them in the hoist, in the motor, and that's some other kind of issue that we can detect with that. But yeah, we need some more sensors.
Question? Yeah, over there.
Hi. It's more a marketing question, but how do you show your customers that there is a return on investment? Because, I mean, your goal is to avoid breakdown. And therefore, how do you show them that you did avoid breakdown?
Yeah, actually, that's a good question. The right answer is to communicate with them. The second part of our promise is transparency, meaning that every intervention we do on their elevator is noted in our system and transmitted to the client. So they have a way of knowing exactly what we did and why their elevator stopped having failures all the time.
Question over there?
I want to know what kind of data do you need to do this, because a supplier of a part can give you all information. For example, in the engine, you have the description of the engine, their functionality. So to do this activity, what kind of data do you need?
Well, so in the case of the system that we deploy today, it's a bit higher level than that. The kind of data that we have will be, for example, the elevator saying that it has had to recalibrate a lot of time, so it can indicate some kind of failure in the sensors that gives its position, or that the doors have opened and closed a lot of time, or that the safety chain is open, that kind of things. We do not currently have actual data on the motor itself, if that's what you mean, or the actual specific components that are in it and what are their nominal behavior, for example. That's something that we will need a bit later on when we add vibration monitoring to the mix to be a bit more precise.
Yeah, you spoke about the next step. Could the next step be to take into account the design of the elevator itself and being able to simulate the physical model and compare it with what happens on the field?
It could be, but I think it would be really, really advanced. Seeing that we have many types of elevators, I'm not sure that's something we'll be able to do in the near future. If you take an example, you can have an older elevator that will be retrofitted in an old Parisian building, and so finding a physical model that actually explains exactly what is happening in this particular elevator will require a lot of tuning, I think. That's not for now a direction we are really looking into, but that could be interesting.
How will you tackle with the fact that the more efficient your algorithms will be, the less breakdown you will have to train your algorithm, and especially you will have less breakdown of a kind you are able to predict?
Yeah, that's the main catch with predictive maintenance. And usually the issue you have with that is that you predetermine thresholds and you do preventive intervention when your sensor value exceeds that threshold, and then you don't know if you would actually have had a failure later down the line. In our case, what's interesting is that our portfolio keeps growing. So when we have a new elevator coming in place, we will be able to put sensors in place quite early on, and the effect of our increased maintenance performance only comes after a few months. So we'll still have some breakdowns in the beginning to keep our model up to date. Or at least I think that's the right approach. We'll see in the coming years how it works.
Last question, which is regarding the elevator manufacturer. So I imagine they have a lot of data. They're producing the elevator, so they can probably also gather the data, and they know how to collect the data or so on. So are there competitors of yours? Are there partners? So that you can maybe better integrate with them and collect the data? How do you see them?
Well, actually, the first point is not really true. They don't have that much data. They are not investing as much into maintenance as they could be. And usually what they do have is a lot of data about new elevators of their specific brand. The interesting part of what we do is we try to cover the whole range of brands that we see in the field. So for now, we mostly see them as competitors because we do the actual maintenance the same as they do once they've installed the elevator.
Okay, well, Axel, thank you very much. It's been very interesting.